So what I want to do in this video is to correct the mistake that I made in class today. That's one big takeaway from this video. And then the last problem I did in class, I want to do a better job at explaining that. So I want to redo that one. Okay, so what we did was come here to this problem right here, 59b. And what came out of that, okay, was that we had this molecule right here. This is what I said the answer was. The answer was we had our methyl right here, carbonyl, a CH2, and then an oxygen and a CH3. That's what I said the answer was. Now, the mistake that I made was describing the chemical shifts. Okay, so let's label. The labeling may be different than what we went over in class today, but that doesn't matter. Let's just correct the mistake. Let's say this signal was A, that's B, and that's C. Okay. Now, a student asked me why I said signal A was further downfield when he's like, shouldn't the C, this one right here, shouldn't that be further downfield because it's connected to the oxygen atom? And if you recall in class, what did I say? I said, no, A is further downfield because of the molecular anisotropy. But molecular anisotropy really has the strongest effect when the hydrogens are directly attached. So for example, like the aldehyde. So an aldehyde is directly attached to a carbonyl, and that is deshielded very strongly because of the molecular anisotropy, and that has a chemical shift around 9 to 10, right? But when you add a methyl group, those hydrogens are now one bond further away and doesn't have a strong as effect as when the hydrogen is directly attached. So if we go back to this table that I gave you, I want you to look really carefully at the different chemical shifts right here. Well, okay, molecule number 6. Do you see how that's a methyl group directly attached to a carbonyl? And it has a chemical shift around 2. In contrast, in molecule 11, you will see that we have a methyl group directly attached to an oxygen, which has a chemical shift of 3.3. So the mistake I made was I swapped those. And so we have to fix that. Okay. Let's see here. Did I use the wrong one? Okay. So we need to fix that mistake. So my apologies, everyone. So what we have is A has a chemical shift around 2.1. C has a chemical shift around 3.3-ish. So we can say now that C would be further downfield, A is there, and B is there. Okay? So that's the correct answer. Now, someone also asked in the discussions that, hey, let's take a look at 59A, okay, and go through that one. So let's do that very in detail here. So 59A, we see the molecular formula. So first thing is we have to do the degrees of unsaturation. So C4H8O2 gets converted to C4H8. 2 times 4 plus 2 equals 10. Minus 8 hydrogens divided by 2 equals 1 degree of unsaturation. We come here, we see a beautiful carbonyl stretch. And so we also go right down the 3000 here and see that we have sp3 carbon hydrogen stretches. Now some might argue that, hey, we have some signal over here that corresponds to some sp2 carbon hydrogen stretches. But you can eliminate that right from the start because you know that you only have 1 degree of unsaturation, and that's accounted for with the carbonyl. So it is impossible to have any carbon-carbon double bonds. And then when we come here, what's the splitting pattern tell us? Well, we have a methylene right here that integrates for 2, and that's a quartet. We have a singlet and then a triplet. And so we have a methylene, which is a CH2, and it has to be attached to something that splits it into a quartet. And one way to do that is one of those X groups right there has to be a CH3. That's the only way that methylene could be a quartet. And then we have, for this signal, we have a methyl, CH3, and that has to be attached to something that gives it a singlet. And so that could be a CH3 attached to a carbonyl. That would give us a singlet, or it could be a CH3 attached to an oxygen. That gives you a singlet. So we're just coming up with possible ideas of what that could be. And then we have a triplet right here that integrates for 3. And that's kind of cool because we have something that integrates for 3 over there. And look, its neighbor is going to split it into a triplet. So there's a good chance that we have something that has a methyl attached to a methylene. Now let's clean this up a little bit. We know the splitting patterns of everything. And so now all we have to do is just kind of just try to put the pieces together. And if I try to do it like this, okay, let's try this one. What if I had my methyl right there? CH2, OCH3. Does that work? Well, that signal A should be a singlet around 2.1. That matches very nicely. Okay. Now I have a methylene right there, sandwiched between an oxygen and a carbonyl. That would go, the chemical shift looks like it would match. But what would the splitting pattern be of that? That would be a singlet, and we don't see a singlet there. And then if we look at this methyl, that should be a singlet, and that's a triplet. So that the connectivity of that molecule doesn't work, even though this molecule right here that I just drew does in fact match the mass spec, and it matches the IR. Okay, so we just have to so we have to try different connectivity. So what if we did, let's see here, what if we change up the connectivity to do a methyl, and then we stick the oxygen there, CH2, CH3, like that. So we'll do that signal A, we'll go B and C. So we have a methyl, and that would be a singlet. And so that's what we see right there. So that's A. And it matches the chemical shift of approximately 2. And then we have another methyl group, B, right there. And this B right here we would predict it to split as a triplet, and that matches. And then our methylene, we see right here, would split into a quartet, which would be right there. So that matches up nicely. And so now, how would the carbon show up? It would be C, A, and B. And we see 4 signals in the carbon-13, so we have that D, that carbonyl carbon, right there, showing up around 170. So that's the answer for 59A. And when you compare that structure right there to problems 59B, you'll see that it's just slightly a little bit different. Same chemical formula, but the chemical shifts and the splitting patterns are very different. So I think that's powerful and cool in the fact that look at that molecule right there and compare it to this one. It looks very similar, but NMR and the data there allows us to distinguish between the two isomers. I think it's very powerful. Okay, now let's go to the very last problem here. Wait, let's see. Someone asked a question about... Let me just take a look real quick at my emails. I want to see, someone asked a question about 60A. So let's take a gander at something. So someone had a question about 60A, so let's take a look at this table. And apparently it's reloading. Let's see if I can open it in the app. See if that makes things go faster. Let's see here. Let's see. Where is that table? Try and find the table where of the chemical shifts. There's one of them. And then this one. Okay, let's take a look at this one here. So this table doesn't help us answer that question. What about this one? Well, that one, that's not going to help us. So I'm going to actually just not worry about that one right now because my main goal was to take a look at this one. This is the last problem we did in class, and I don't feel I did it well enough. I can do a better job with that. Okay? So let's take a look at that one. So what's the first step when you see this here? We need to calculate the degrees of unsaturation. So we see C4H6 would be the formula here, because what do we do with oxygens? We just ignore that they're there, right? So 2 times 4 plus 2 equals 10 minus 6 divided by 2 is going to give us 2 degrees of unsaturation. Now, that's helpful because what do we see here? We see a beautiful carbonyl right there. So that accounts for 1 of the degrees of unsaturation. Another thing that we can see is if we go right down 3000, we have some signal right there. So that implies that we have a sp2 carbon-hydrogen bond stretch right there. And so that implies that we have some alkenes. But just to make sure that that's correct, where would we expect a carbon carbon double bond to show up. Right there. There it is. So there's our carbon-carbon double bond stretch. And there's our carbon-hydrogen stretch. We're an sp2 hybridized carbon. So I'm feeling pretty good that we found this guy. That's 1 degree of unsaturation. And then this guy is the alkene. So those are some ideas that are flowing in my head. Now when I come to the NMR here, okay, what do I notice? I have 1 signal, 2, 3, and 4 signals right there. Now, how many carbons did I have in this thing? Did it say? Let's rewrite it. C4, C4H6O2, and I need 2 degrees of unsaturation. I'm very confident that I have a carbonyl, and I'm somewhat confident that I have an alkene based off of that data. Okay. Now how do we tackle this? We have 4 carbons. So when I see this guy right here, I have a, what's that? That integrates for 3. So that would be a methyl. And that methyl integrates, or sorry, splits into a singlet. So we have this singlet, so that means the methyl has to be attached to something that has no hydrogens attached. Okay. And then we have a doublet of a doublet right there. So what have we seen splitting doublets of doublets? Well, I have an idea that we have an alkene in the molecule. So what if I had a alkene like this? Those 2 signals, or those 2 protons right there, those are not equivalent to one another. So HA would be split into a doublet, and HB would be split into a doublet. So I see that I have 1 of them. So that would account for 1 of the doublets of doublets. This one would count for the second doublet of doublets. And then we have, let's say, HC. HC would also be split into a doublet of a doublet. Something else that's screaming at me is that we have chemical shifts around that region where we would expect some alkenes. So that the chemical shift also helps me to say, hey, that kind of matches the IR data that we have alkenes there. Okay, and also, what else do we have here? We have some carbons right here that are pretty far downfield. That could also imply that we have some alkenes. So that's what I'm going off of, and now I'm just going to try to put the molecule together to see if I can make it match the NMR. Okay, so what if I just look at my alkene? I'm going to erase this here. What if I have my alkene? We have some hydrogens. And then I have a oxygen. And something like this. Okay? Now, I see that the methyl here does in fact give a predicted singlet. And then we will say that C, A, and B, okay, and we could see that those are going to be predicted to be doublets of doublets as well. So that matches my NMR. Now, yeah, that works out perfectly right now. So we can definitely say with surety that we'll call that proton D Okay. D is definitely that guy. We can definitely say that for sure. But now, how do I know how to assign A, B, and C? How do I know which order it is? And that's where we have to look at the J coupling values. Okay, and the J coupling values is going to show us the connectivity. So when I take a look at the J coupling value here, 10 Hertz, that is telling me that I have a cis coupling. And then a J coupling of 16 is telling me I have something that's trans. In that range, that's going to be geminal, and that's going to be trans. That's geminal, and that's going to be cis. So now I have these relationships here. So this signal right here has a cis coupling, J coupling, and a trans. And when we go to our predicted molecule down here, which letter or which proton has a cis coupling and a trans coupling? Well, we see that C right here, HC, is cis to A and trans to B. So that would make this proton C. Then if we look at this signal right here, that goes for that one. What do we have? A geminal and a trans. So HB is geminal to HA and trans to C. So that signal would be B. And then A, proton A, is geminal to B. A is geminal to B, but cis to C. So that has to be proton A. Just like that. So when we do, and so when we go to look at the carbon-13, we can see that D is the furthest upfield. And what is the furthest downfield? That's the C proton. Okay. Well, okay, now we have to take a little step back here. Now we have to really evaluate our carbonyls here. So let's say this guy right here, let's give it a letter of E. Okay. And then let's give this a number of 1 and a number of 2, because we got a lot of letters going on right there. Okay. So what we have here, where would we expect carbon E? That is a carbonyl carbon, so that has to be the furthest downfield. Okay. And then the next one, it's only really between these two right here. Those are the two left that we have. And we see that carbon number 2 is next to an oxygen atom. So that has to be carbon number 2, and that's carbon 1. Like that. So that's how you would annotate that. Now, someone asked a very good question about drawing a other structure that looks like it will work. And good job if you came up with this structure right here, okay? Let's say if you had our CH3 attached to an oxygen like that, and then we did it like that. Let's see, is that what someone came up with? Now I'm drawing a blank. Yeah, I think they just swapped the two ends there. Is that what they did? To O. Like that. 1, 2, 3, 4. Yeah, that's the structure that some people came up with. And they're like, hey, if I look at that hypothetical structure, what would I predict the splitting patterns be? We'll call that A, B, C, and D. What would the predicted splitting pattern be for A? Doublet of a doublet, doublet of a doublet, doublet of a doublet, doublet of a doublet. Wait, D, what? That would be a singlet. That matches everything, doesn't it? So how do I know the structure that I proposed right here? How do I know that one's correct and this one's not? Well, that's a tricky question, but we can figure it out. And it boils down to chemical shifts, right? And that's kind of the mistake that I made in class today that I'm trying to rectify now. Where would we expect a methyl group directly attached to a carbonyl to come up in the chemical shift? 2.1. Where would we expect a methyl directly attached to an oxygen atom to show up? 3.3. So when we go to our proton NMR, where is that singlet? It's at 2.1. So based off of the chemical shift, the only difference between these two structures that I've drawn and how you could differentiate them, because the mass spec is going to show you pretty much the same stuff, the IR is going to kind of show you the same stuff, but the chemical shifts in the proton NMR, that one signal right there, that's going to help you know the difference between which structure. So that is the structure, predicted structure. That is the correct one. And if you got this one below here, good job. You got very, very close to it. But that's how you know the one on the bottom's wrong, due to that chemical shift. So I hope that's helpful to you, and good luck on your test that's coming up.